My name is Steve Banwart. I'm a professor here at University of Leeds. I'm director of the Global Food and Environment Institute. I'm also Dean for Global Development for the university. My own science area is in soil and water resources, and my core science is chemistry. So I'm thrilled to be the chair for this soils presentation today. It's my pleasure to welcome you to this virtual seminar of the Institute. The title is Sounding Out Soil, and it's presented by Professor Megan Povey, who's professor of food physics in the School of Food Science and Nutrition at the University of Leeds. If you're not from the university, you may not know, but I'd like to say that the School of Food Science and Nutrition is one of the crown jewel departments of the university, routinely ranked in the top 1 or 2 in the UK. It's one of the top schools in food and nutrition in Europe. Megan is a physicist who has worked with food for over 4 decades, developing novel ultrasound and acoustic methods for food characterization and processing. Most recently, in collaboration with colleague Jen-Shi Chen, she has highlighted the importance of sound in the human appreciation of food. She is a designer, together with Philip Nelson, of several instruments for analyzing food and its stability, including the Cygnus UVM ultrasound velocity meter and the Acoustiscan scanner. She is also co-inventor of the Ultracane blind aid. Currently, professor of food physics, collaborating with colleagues from the Faculty of Medicine and Health on acoustic imaging, and also working with colleagues from Nottingham, Newcastle, Cambridge, Valencia, and Madrid universities. She has welcomed many visiting students and overseas colleagues to her laboratory. For a bit of background about who we are more broadly, the Global Food and Environment Institute is an interdisciplinary research community which brings together members from across academia, industry, and public policy to work on the integrated challenges of food security, climate change, and dietary health. And for further information, we please invite you to visit our website at www.leeds.ac.uk/global food. And this seminar is part of a series, so please check out the chat function with a link to our series advertised on Eventbrite and our Twitter feed for more information. Before I introduce Professor Povey, I would like to remind you of the seminar etiquette. Please ensure that your cameras and microphones are switched off for the duration of the seminar. The presentation will take about 20 minutes, during which please use the chat function addressed to everyone with your questions. And at the end of the presentation, there'll be a 10-minute Q&A session where I'll collate questions from the chat function for Professor Povey. May I remind you that the seminar is being recorded and a recording will be made available on YouTube. And so now I pass over to you, Professor Megan Povey.
Thank you, Steve. Welcome, everybody. My name is Megan Povey, and Steve has described quite well some of the things I've been doing for a number of years. In addition to being a physicist, I'm also a chartered engineer, so part of my bag is actually manufacturing machines and machinery, particularly prototypes. So moving quickly on to the subject of the talk, I'm going to talk about sounding out soil, and this involves using ultrasound and acoustic methods for characterizing soil and its denizens. So let's without any to-do, move on to the introduction. So soil is extremely important. Some sources say that there are only 50 cycles of harvesting left in the soil globally, and this is due to intensive agricultural practices, which are in effect destroying soil structure. And in some cases, the soil is totally destroyed, becomes sand and desert. So it's what we're interested in is what can we learn from both active and passive acoustics. In active acoustics, we generate sound, and then we listen to what happens to the sound that we've generated. So we know what we're generating, and then we can compare what we've generated with what we get back to learn about the material through which that sound has traveled. In passive acoustics, you simply listen to the sound, but we listen not just in the audible range in which we as humans exist, but infrasound and ultrasound as well. In order to understand what it is we'd like to learn about soil, I'm going to talk about some measurables: porosity, compressibility, and also I'm going to distinguish between mobile water and bound water. So total water content is not necessarily a very useful quantity, because a lot of the water is bound to the surfaces of the soil particles and is actually unavailable for plants. We're also interested in listening and understanding about insects, small mammals and invertebrates, all of which make sounds, and many in the ultrasound. And I'm going to talk about passive acoustic techniques ranging from 2 hertz, that's infrasound, to 200 kilohertz, that's ultrasound. Interestingly, also, bacteria and fungi play an important role in soil structure. The speed of sound in soil, which is mainly what the technique we've been developing on the university farm near Tadcaster, the speed of sound depends on volume fraction of material, not mass fraction. So if bacteria and fungi begin to grow in the soil, they actually expand the soil, they push the soil particles apart. And one really fascinating thing that I've learned since starting to work in this area is that plant roots actually signal bacteria to grow. And by growing, the bacteria expand and ease the path of the roots between the soil particles and the solid soil particles. So we need a model of soil in order to understand the interaction between sound and soil, and also in order to quantify the important things that for plants, like the mobility and the porosity. And we can go from one extreme, which is a dry powder, which a desert without water would comprise. That same powder, if water is added to it, so that's a wet powder. And then we move on to porous, dry, healthy soil, and then porous, wet, healthy soil. And the question is, can we differentiate healthy soils from degraded soils acoustically? So first of all, the technique that we've developed on the university farm involves what's called, well, we use 2 techniques. The upper diagram is an illustration of pulse echo. So to understand pulse echo, if you imagine you're standing in a canyon with your back to one canyon wall, and then you shout, you will hear an echo of your shout coming from the far canyon wall. And this is what we do in our instrumentation. We generate a shout. That shout will be 1 million cycles per second, let's say 1 megahertz perhaps, and might last for just a couple of millionths of a second. So this is a very fast shout, but it does allow us to make very accurate measurements of the speed of sound, because if we know the distance between the source and the reflector, then the pulse, the shout, has traveled twice that distance up there and back. So we know the distance, and if we measure the time, then the speed of sound is just distance divided by time. And the first experiments on the measurement of speed of sound were done in Geneva, Lake Geneva, by two guys called Culloden and Sturm, who used a bell, which one of them in a boat struck under the water, and at the same time, I'm not sure how he did it, but caused a flash of light with gunpowder, and his colleague on the bank started the watch when they saw the flash and stopped the watch when they heard the bell. Another arrangement, which is the one we're using on the university farm, is where we have two transducers. One is a transmitter and the other receiver. And in this case, we measured the time just as before, but this time the distance is just the distance between the two transducers. And at the bottom is an illustration of the amplitude, the sort of amplitude against time that we get from the signals that we're creating on the university farm. Now, I'm not going to go through, I put a bit of maths here, apologies, but basically we can work out composition from the speed of sound using what's called a mixing rule. So we can obtain the volume average of the components in the, sorry, when all the components of the soil contribute towards the speed of sound in this kind of volume averaged way. And I've just lost a diagram somewhere. Sorry about this, but oh, I know. Sorry about, yep. I've lost a diagram. What's happened? I'm sorry. Apologies, folks, but I've got a very important diagram that appears to have disappeared from my slides, which is very weird. So it's a very important slide. I'm just going to stop sharing and
Megan, while you're looking, I'll also have a look at the slides that you forwarded to me yesterday or the day before, just in case.
Yeah, anyway, I've found it.
Okay.
No, well, that's very weird. It's in the presentation, but it's not coming up on the display. So that is a Windows. Okay, I'm going to show my, right, I blame Bill Gates for this, I have to say.
Megan, is this the slide with the hand drawing of the soil particles?
It is. It's that.
Do you want me to share? I have this slide up. Do you want me to share it briefly and then we'll go back to your presentation?
Well, I can bring up the non.
Okay, there it is.
Okay, all right. Hey, I've just been. That's a Windows gotcha. Right, so this is my acoustic model of soil. So we have the silica particles, which are in black. And what people don't know about silica is that silica is very effective at binding water. So you have a monolayer of water around every single silica particle. And it's very, very difficult to remove this water. Even taking it to very high temperatures, it's very tightly bound. And that actually, that water affects the dielectric properties of the mineral components. Then we have voids, and these air pores some of them will be filled with water, or they may not be filled with water. And this is where the water content of soil changes most dramatically. It's through the filling and unfilling of these pores that allows water to be mobile and move around in the soil. And then there's the organic material is extremely important, because it's the organic material which includes bacteria, plant material, and so on, which binds the soil together. And it's the degradation of this organic material by intensive agriculture, which is destroying soils. So we really would like to know more about this organic material. Now, these different components have very different speeds of sound. So the silica particles have a speed of sound at around 6,000 meters per second. Just to give you an idea, the speed of sound in air is around 340 meters per second. So it's 20 times lower than silica, the air pores. The water has a speed of sound around 1450 meters per second. And the organic material itself will have speeds of sound that vary between about 2,000 meters per second in wet organic material to 500 in dry organic material. Right, so I need to go back to my presentation now. It really doesn't want to show it. Okay, right, so moving on. Right, so what I'm arguing is that from measurements of the speed of sound, we can tell a lot about the composition of the soil. And by the way, Steve, can you please shout if when I'm getting near to the end of my time? I tend to get carried away a bit. Okay, so here is a table of these components: silica, organic material, water, and then the properties of the combination that comprises soil. So here are the speeds of sound in these different components. And then here are volume fractions. So we're here 40% silica, 40% organic material, 10% water, yes, and 10% air as an example. And then here are the different densities that we would expect. And we can also work out the compressibilities. And from our model, we would then predict in this soil a speed of sound of around 29 or 30 meters per second. So very slow. Now, if we move on now, here's a plot of how the speed of sound in that soil would change if the water content is changing. So we can see that the speed of sound will change by over 2 decades between no water, that is no mobile water, and 20% volume percent of the material being water. Now, we can't get higher than 20% in this soil because of the volume occupied by the other components. So the idea on the farm is that we can actually measure the speed of sound in the soil without taking samples, actually live. So we can also do measurements for determining soil density. So this potentially gives us a method for getting the porosity. This method actually involves sending the pulse of sound through the air above the soil and bouncing the sound off the soil surface. So here we are on the Leeds University farm, and this is in the wheat field this summer. And so bottom right, you can see a picture of us in the middle of the atmospheric observatory, and we can see one of the devices that is collecting the gases generated by the wheat. So we walked around in this wheat field and we measured the speed of sound through the soil. And as you can see, we don't have to dig the soil up. We can do this simply by placing the transducers on the ground. You can see they're quite large, they're quite heavy, and they're very robust. And again, we can make these measurements actually on mown grass as well. So this is one of my colleagues actually measuring the speed of sound in a mown field this summer. And so I apologize for these sketches, but these are the sketches I did actually on site, because what we discovered was that we could measure the depth of cracks in the soil, because my colleagues were very keen that we did measurements in the lab on various model soils, and I'm saying, hey, I just think it's going to be so different out there on the farm, and it was. And what we saw are these cracks. So you can see a crack in the soil, and what's happening is complete blocks of soil move together, and these cracks appear. And what we discovered was the time it took the pulse to travel across the crack was much, much longer than the time it took for the sound to travel parallel to the crack. And the reason for this is that the sound was going below the crack, so it was traveling a much longer path. So we could actually, by comparing the measurement of the speed parallel to the crack with the speed across the crack, we could work out the depth of the cracks. And this was the sketch that we did, and an actual estimate that are made at the time in the field. So all these measurements can be done in the field. Now I've lost another. Was my robot gone? Okay. Right, well, all this kit has been attached to a robot. And if I got time to show you, I'm just going to stop sharing and see if I can find my robot pictures. That's very... This is quite... I'm sorry, I just... It looks to me...
I don't find one in the slides that I have, or the copy of your slide deck, Megan.
Right, warthog. Okay, I know this is embarrassing, but I'm going to find this. I'm just going through my file store, and I know where everything is. So smartphone. Okay, I'm going to share my screen again. She says confidently, but why? Okay. So you should be able to see that.
It's not come up yet. At least not on my screen.
Oh, that's big. Yep, here we go.
Something came up. There you go.
Okay. Right. So so this is the implementation of the ultrasound system on the robot. And so these two lifting arms that place the probes onto the soil, and then the measurements are being made automatically. The robot's being driven from a website, and the data's collected automatically. The only problem that we had with this is that at the moment you put that in the field, the electronics gets hit by clods of soil, and so it's going to have to be ruggedized. So here's some more images of the system and the electronics. We've also got a video of it working, but I'm not going to show that. Okay, so I'll just stop that share and go back to the presentation.
Megan, you've got about 5 minutes left for your remaining slides.
Okay, thank you. Okay, right, so that's the active part. I've only got 5 minutes to talk about passive acoustics, but we're interested in combining a range of measurement modalities, including gamma ray detection and using passive acoustic measurements. And this is, for example, this is a broadband ultrasound receiver designed for recording bat signals. It actually goes up to 120 kilohertz. It's quite an impressive piece of kit, and it will just plug into your into a Windows device. Below is a picture of my system, which goes up to 200 kilohertz. The microphone is actually just, I'll just show it you. It's tiny. So there's the microphone just at the end. So the idea is that we combine the active ultrasound together with passive ultrasound. And the guy who's done the most in this area is David Chesmore at York. And you can identify species, you can identify diversity because the bigger the range of different sounds that you're picking up is a sign of biological diversity. And that's my talk. Not most wonderfully given talk, but hey. And
that's great. That's great. Thank you. Thank you, Megan. And we have questions in the chat. I'll pick up a few of these. There was a couple of questions about the probe volume for the measurements in the soil. How deep is what is the depth of soil that you're probing? In other words, the questions were specifically around soil densities. What is the depth to which you would be getting a measurement of soil density? Okay. Is it top 10 centimeters, or how deep?
It'll be the just at the top. It makes a big difference. You know, if the soil is very wet, then the surface layer gets the soil that is penetrated by the sound, because we just measure the sound that travels the shortest distance, and it's quite a complicated question. There isn't a very simple answer, but the first top centimeter or so, our probes are working at around 20 kilohertz. So it depends on the wavelength and the speed of sound.
And just on that, does it depend as well on how far apart your transducers are, or is that, how do you decide?
Well,
the sort of physical configuration.
Okay, well, we measure the speed of sound by detecting the first arrival. It's basically the shortest acoustic path, which we assume is just a straight line between the two probes. If we look, we can look later on in the echo. If you remember, I showed the trace, which is quite long, and that's because sound comes from other parts of the soil, but it takes longer. The arrival times are later. So potentially we can learn about different depths by looking at the data that's arriving later on in the signal. But the interpretation of the data depends an awful lot on the nature of the soil. So I wouldn't like to make any generalizations, except to say that potentially we can see into much greater depths than just the 1 or 2 centimeter surface layer. And of course, the measurements on the cracks showed that. I mean, that was, we were going down about 0.5 meter in the soil on in the Hanger field at the university farm.
So we do have a question about the mathematics. I had this question in my own mind as well. It is in the soil model that you have in the equation, that translation into your equation for the sound propagation, you talked about 4 unknown volume fractions, like the mineral fraction, the air-filled pores, water-filled pores. You're doing, one pathway for the weighted speed of sound. How do you solve that single measurement for those 4 components? And it was noted that if you have wet and dry organic matter, that would add a 5th one, in fact.
Yeah, okay. Well, right. Now the equations. The speed of sound is 1 divided by the square root of the product of the compressibility and the density. Our mixing rule takes a volume average of the compressibility and a volume average of the density. So that can only be solved if we've got 1 unknown. So we have to know 3 out of the 4 volume fractions if we're solving for volume fraction.
So in your analysis, did you then presumably did some independent measurements from soil samples?
No, I just solved this in an Excel spreadsheet by keeping the amount of silica and the amount of organic material constant, and then I just changed the ratio of air to water and solved for the speed of sound. Okay. That's what produced this graph here.
Okay, but you'd need to have an independent measurement of your silica and your organic matter. Okay.
Yes, you'd need to know the dry matter composition.
Okay.
Yeah.
We have time for one more question, and there's a couple that I think fit together. One of them is what are the next steps for this research? In other words, I guess, could you consider this exploratory or proof of concept? What kind of, where is this at in terms of research versus, you know, application?
Yes.
What would be the next steps? And is this tech ready to be used outside of the research environment, for example, by farmers and agronomists?
Yeah.
Or
Okay.
what would be the path ahead for you to move it in that direction?
Okay, right. Currently, it won't work on the farm because we will have to ruggedize the electronics. So the next step is to ruggedize the electronics on the Warthog robot. We can control the robot. Its position is recorded in GPS. We're collaborating with Durham on making gamma ray measurements, so that hopefully by the beginning of next year, we'll be able to move around the hangar field, which is instrumented with moisture detectors. So we've got the whole field has got moisture detectors. So we can move around in this already instrumented space. And hopefully we'll be able to publish the data to show that this technique is viable. And then if it is, then it wouldn't be very difficult to make it into a commercial package that farmers could use. I mean, the ultrasonics is already available off the shelf. It's just the software and the kind of software engineering of it that's and the ruggedization and then commercial packaging to make it viable for use in farming anywhere in the world.
Okay. We had one final question I'm just going to pick up because it is related a little bit to the last couple of bits of discussion that we had. The question is that given that you need to know most volume fractions, maybe this is best to be used as a soil moisture sensor, which would allow you to average soil moisture over a path of say 2 to 3 meters of travel, you know, which would be at different scale of averaging than point sensors like soil moisture probes with a volume of a few cubic centimeters that go into the soil. Do you have a view on that?
Yeah. So I think that's right. I think with all these techniques, you do the obvious and simple list thing and the thing most likely to work first. And if it works, then basically you've already got a infrastructure which you can then begin to build on to perhaps using artificial intelligence, you know, multimodal sensing, and begin to build a package which is much more informative. But I agree, you start with the moisture is the obvious thing to be going for, yes.
Okay, I'll draw questions to a close there. Just remains to thank you very much, Megan, for this great talk. We look forward to hearing about the technology as you develop it. And thank you everyone for joining, particularly those of you who joined us from outside the University of Leeds. It's great to have you with us. Thank you very much. And thank you again, Megan.
Bye.
We'll close the meeting with that. Thank you.